A third method to prepare an alcohol is by the reduction of a carbonyl. You'll recall that a carbonyl is a carbon doubly bonded to oxygen present in a ketone. It could be an aldehyde in an ester, and in carboxylic acids. So what is a carbonyl? Now, reductions involve a change in oxidation state. So in general chemistry, we learned about oxidation and reduction. When you learned oxidation and reduction, you either learned oil rig, maybe as a mnemonic. Oxidation is loss of electrons. Reduction is gain of electrons. It's a gain of electrons, and it's actually a reduction in positive charge. So gaining an electron reduces the positive charge. So it's called a reduction. We will calculate oxidation states, and this is kind of a bookkeeping methodology. When we calculated formal charges, that was a method of electron bookkeeping. And in the case of formal charge, when we looked at a bond, each atom was assigned half of the electrons in the shared pair. So here's the question: what is the formal charge on carbon in methanol? So in the next slide, we'll look, what is the formal charge on carbon in methanol? So here's methanol, CH3OH. So when we learned to calculate formal charge, there were two things we needed to do. One was to look at the periodic table and see the correct number of valence electrons for the atom we were looking at. And the other was to look at each bond and split the electrons equally between the bonded atoms, so that equivalent to homolytic bond cleavage. So in the case of methanol, when we're calculating formal charge, we go to the periodic table and we see that it's a group 4 element, or group 14, depending on which numbering scheme you're looking at. So there are 4 valence electrons for carbon. If we split each bond homolytically, then carbon has 4 electrons, and the formal charge is 0. When we're calculating oxidation state, there's a difference. With oxidation state, we treat all the bonds as ionic, and we break them heterolytically. So we don't do the equal sharing of the electrons. And when we do this, we assign ownership for that pair of electrons to the most electronegative atom in that 2-atom bond. So in the case of the carbon-oxygen bond, the electron pair is assigned to oxygen. Now let's look at a few more examples. So we just did methanol, and we calculated correctly a -2 oxidation state. If we look at methane, we have carbon, each hydrogen assumed a positive charge. The electrons are given to the most electronegative element. So carbon has all 8. So it is 8 electrons assigned in this bookkeeping method, with 4 electrons, 4 valence electrons for the atom. So there's an excess of 4 electrons, which gives us our -4 oxidation state. So we've done methanol, methane, methanol. Looking at formaldehyde, if we have carbon, the hydrogens and the oxygen, we see that carbon has 4 electrons in this bookkeeping methodology with a valence requirement of 4, so the oxidation state is 0. So hopefully this follows, and you recognize that formic acid and carbon dioxide would give +2 and +4 respectively. So in an oxidation reaction, we're increasing carbon's oxidation state. So looking across this series, let me see. Sometimes when I'm making these videos, I don't know when my pointer is visible. When we're going across this series of reactions, carbon's oxidation state is increasing. So methane going all the way to the carbonyl, so methane to an alcohol, to a carbonyl compound, to a carboxylic acid, all the way to carbon dioxide. This is a moving in the direction of oxidation. In a way, you can think of it as adding oxygen, although that doesn't really hold up. You're adding oxygen to methane, but in the case of methanol formaldehyde, the number of oxygens aren't changing. Reduction can also be thought of as adding hydrogens. So you're breaking carbon-oxygen bonds and replacing those bonds with carbon-hydrogen bonds. So now we recognize that we can convert a carbonyl to an alcohol using a reducing agent, an agent that affects the reduction on the substrate, going from a carbonyl to an alcohol. The reducing agent is itself oxidized in the process. This results in the addition of hydrogen across the pi bond. So we're going to talk about 3 different reducing agents, or 3 different approaches: catalytic hydrogenation, the sodium borohydride reduction, and using lithium aluminum hydride as a reduction. And each of these has some advantages and some potential disadvantages, so we're going to talk about that as well. So we're going to talk about 3 reducing agents that can be used, and the first of these is hydrogen itself with a catalyst like platinum, palladium, or nickel. Now, when done at large scale, these reactions are typically done at high temperature and under a elevated pressure. You can do atmospheric hydrogenations on small scale in the lab. They pose a significant fire hazard. The catalysts, the used catalysts especially, are often pyrophoric. So a lot of procedural effort is put into place to prevent exposure to air when you're doing an atmospheric pressure hydrogenation. Also, because there is such a high risk of fire, typically, and you have metals present, you need a fire extinguisher that's capable of putting out a metal fire. So a Class D fire extinguisher, often that might just be having a significant quantity of sand that you can smother the fire with sand. And often these are done in flammable solvents, so the hood is cleared of any unnecessary materials, and solvent is never poured from the reagent bottle into the hydrogenation reaction when it's done at atmospheric pressure. A small quantity is put into a beaker or an Erlenmeyer flask, and only the quantity that's necessary for the reaction is brought into the hood. So more commonly, a hydrogenation reaction is done under pressure. I'm going to show you a little video clip within this video just to show you what a hydrogenation apparatus looks like, so that if you ever see one, that you're better able to get started with it. So this is a hydrogenation apparatus. I'm going to run the video in a second. There's a motor here. The motor is connected to a wheel. The wheel is connected to a rod. So the rod goes back and forth and rocks this. Here is the actual reaction vessel. It's made of glass. For higher pressures, it would be made out of stainless steel or an alloy, Hastelloy, something relatively unreactive. This pin, this cradle swings back and forth. This is the pressure gauge for the inlet hydrogen. I'm not sure if the sound on the video is going to come through. They're going to mention this is an explosion-proof motor. Pet peeve of mine. Explosion-proof means that it will not be the source of the explosion. It doesn't mean that it's going to survive an explosion. Explosion-proof motors are usually hermetically sealed, so any sparking from the brushes in the electric motor cannot mix with the atmosphere in the room, so that it's not a spark source for hydrogen gas in the room. Explosion-proof also means that it is hardwired. You see this cable here? This one still has a plug somewhere, but usually when you have an explosion-proof installation, there's no plug. An electrician has come in and connected it to the wiring of the building with no plug, because the plug itself becomes a spark source when you plug it in and unplug it. So that's what's meant by explosion-proof. So this is a company that resells, I don't think the sound is coming through for you. This is a company that resells instrumentation, and this video is on YouTube, basically promoting the items. This shield goes around the apparatus so that if there is a rupture, that large shards of glass don't go flying through the room. This gauge is in pounds per square inch, I believe. Yeah, PSI. So running at just below 60 PSI. They're not running a reaction. They're just demonstrating that the piece of equipment is functional. So that's what a hydrogenation apparatus would look like for a lab scale reaction. So I said I was going to mention 3 methods of reducing carbonyls to alcohols. The first was catalytic hydrogenation. The second is the use of reagent sodium borohydride. It's a common reducing agent used for aldehydes and ketones. So sodium borohydride is a white crystalline solid. It's soluble in protic solvents, also low molecular weight alcohols, water. It does react with protic solvents, but relatively slowly. So that's worth noting. So in the sodium borohydride reduction, the reagent is a source of hydride ion, H negative, which will add as a nucleophile to the carbonyl column, to the carbonyl carbon, followed by a proton transfer from the solvent, which we see depicted here. The nucleophilic attack, the movement of the electron pair onto the oxygen, which allows for the abstraction of hydrogen from the solvent, in this case methanol, and that alkoxide ion is protonated to produce the alcohol. Now, when the ketone is unsymmetrical, the left half and the right half are not identical. This results in the formation of the alcohol, as well as addition of a hydrogen through that hydride. And the transition state is planar, so the nucleophile can attack from either side, so 2 different stereoisomers will be obtained. So looking at that stereochemistry from this figure, if we imagine that this R group is coming out of the plane towards us and this R group is pushed back behind the plane, then the hydride ion is attacking from the right-hand side to give this intermediate And then if the attack were from the left-hand side, the opposite isomer would be obtained. Now, the third of the three reducing agents that we're talking about today is lithium aluminum hydride, or LAH. LAH is a stronger reducing agent than sodium borohydride. The structure of lithium aluminum hydride is similar to sodium borohydride. As I mentioned, the LAH is much more reactive than sodium borohydride. We said that sodium borohydride would be useful in reducing aldehydes and ketones. We can't use lithium aluminum hydride in the presence of a protic solvent. The proton source has to be added after the carbonyl is reduced, so it's two steps. Lithium aluminum hydride delivers the hydride ion to the carbonyl. So again, we have you'll see the similarity that we can generate the two isomers for an asymmetric ketone. But after that reaction is complete, then the alk oxide in the workup step is water is introduced to protonate the alk oxide and consume any unreacted lithium aluminum hydride. And typically this is going to be done dropwise because it's an exothermic reaction and will generate hydrogen gas. Our two hydride delivery agents, sodium borohydride and lithium aluminum hydride, are selective for the carbonyl group, whereas hydrogenation is not. So in this example, we have this seven-membered ring. So it's cyclohept. This is one. Oh, sorry, my cursor doesn't show here. This is 1, 2, 3, 4. So this is cyclo. So I start to say this is a cyclohept 4-ene 1-one. When we perform catalytic hydrogenation, both the alkene and the ketone are reduced in very good yield. When we use the hydride delivery agents, either sodium borohydride or lithium aluminum hydride, we selectively reduce the carbonyl, but do not reduce the alkene. So the reactivity of the hydride delivery agent can be tuned using different derivatives with varying R groups. It's difficult to handle lithium aluminum hydride even at lab scale. In large scale, lithium aluminum hydride is not used because of the handling and reactivity issues, and these analogs are common for large scale reactions. You don't need to know that for any quiz or anything, but just recognize nobody's charging a 1,000 liter reactor with lithium aluminum hydride. So we looked at catalytic hydrogenation, which is going not to be selective, will reduce our alkenes. Lithium aluminum hydride is strong enough to also reduce esters and carboxylic acids, whereas sodium borohydride generally will not. When we reduce a carboxylic acid or an ester, we're going to produce the primary alcohol. Now, in the case of the ester reduction, we're going to require two equivalents of the hydride. The first two steps are a reduction from the ester to the aldehyde. And that aldehyde is subsequently reduced to the alcohol, as we've just gone over. So that's shown in this schematic here, that the hydride adds to the carbonyl, and we have the methoxy group leaving. Normally, the methoxide would not be a good leaving group, but the intermediate is a high energy intermediate, and it's rearranging to form a stable aldehyde. So that's the explanation for that reaction proceeding. Once the aldehyde is formed, a another lithium aluminum hydride moiety will come and add hydrogen to the carbonyl to give us the alk oxide, which in a workup step, we would dropwise add water to have proton transfer from water or from acidified water